Hi, everybody. Today we're starting our second unit. We're doing a lesson on the fundamental counting principle. It's our first lesson in our organized counting unit. So let's get started. So it's a bit of motivation. Let's think of going to a restaurant here. It's Wendy's, and it's got like a simplified menu here. But let's say you have three different options for get a burger, like a combo. You have fries, salad, baked potato, more bacon. It's four options for a side. And for a drink, you could get a soft drink or you could get a frosty. It's two options. So how many meals could you order? Might be a worthwhile question asking. If you want to take a moment and pause the video and think about that, or maybe think of a way you could organize this problem to see how many meals could be ordered, you can do so. And we'll definitely come back to this question later. You may also have noticed throughout your life, like there's lots of different formats of license plates in Ontario. Back when I was a kid, we had the original 3 letters and 3 digits. And then moving towards more recently, 4 letters and 3 digits. Now you might actually see 2 letters and 5 digits driving around, but their new formats are required over time. And maybe you've wondered, why did they change formats? Is it just because, or is there some valid reason? So we'll come back and talk about this one as well. The techniques for counting possible arrangements or outcomes, such as how many different, meals can you make, or how many different license plates can you make of a certain pattern, are really useful for a wide variety of applications, like computer programming. I've got some others there. A city planner, planning for traffic flow. The techniques we learn in this unit can be applied a wide variety of places. So let's do another restaurant question. So let's say we have these options for a 3-course meal. For your appetizer, you can pick soup or you can pick garlic bread. For your main course, you have 4 options: roast beef, pork tenderloin, trout, or chicken wings. And for dessert, you can have chocolate cake or rice pudding. So one way to illustrate all the possible options is to make a tree diagram. We actually made quite a few of these in our last unit with probability. So going to select my pen and let's make a tree diagram. So we'll just start with the top here. We can get soup or salad. For appetizer. For our main, we can branch off 4 different ways. So 1, 2, 3, 4. 1, 2, 3, 4. And what were our options for mains? We could have roast beef, pork tenderloin, trout, or chicken wings. So roast beef, pork tenderloin, trout, or chicken wings. And we have one more layer to add for dessert. For dessert, we could have chocolate cake or rice pudding. So branch off, chocolate cake, rice pudding, cake or pudding. By making a tree diagram, we've shown how many possible meals you could have, just how many possible branches there are. And if you count up the number of branches we have at the bottom, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There are 16 possible choices. Now, our goal for today is not to have to do a tree diagram for a problem like this. We want to develop faster ways. So each branch represents one possible meal. So we can see that we got 16 possible meals. And if we want to see how we get that result without a tree diagram, check this out. So we have 2 possible options for an appetizer. We had 4 options for our main course, and we had 2 options for our dessert. And if we think about each layer, we're kind of multiplying by that number. We've got 2 times 4 times 2, 16 possible meal combinations. So a shorter way of doing that, 2 times 4 times 2, 16 different options. So the principle we just used there has a special name. It's called the fundamental counting principle. You also might see it in different resources as the multiplicative counting principle. And it says this: if one event can occur, we'll say in m ways, and a second event can occur in n ways, then together they can occur in m times n ways. So I might actually flip back to our first slide. So we could apply this to the Wendy's problem. So we had 3 options for burger, 4 options for our side, and 2 options for drink. And so with this particular menu, you'd have 24 different options. The fundamental counting principle, or FCP, is really easy to apply. So let's get some practice applying it. So let's look at the license plates. So with the current format of 4 letters and 3 digits, so I like setting it up this way. So letter, 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 digit, digit, digit. We can use the fundamental counting principle to see how many plates are possible. So for our first letter, there are 26 letters in the alphabet, 26 options. For the second letter, also 26 options. In fact, for each of the letters, if you can repeat them, there are 26 options. And for the digits, you have 10 options, the digits 0 through 9. So 10 options, 10 options, 10 options. So very quickly and efficiently, we can see how many different plates are possible to be made using the fundamental counting principle. So it's pretty powerful, allows us to do some pretty complex questions very quickly. So if you try that with me, you can see it is a lot of license plates. It is about 456,976,000 license plates. If you actually ignore the, so if you just do letter, 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 digit, 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 it'd be the same calculation, just without one of those 26s. So you can try that too. You can see we'd have 17,576,000 if you try that out. Now, that's still a big number, but if you consider maybe there's 10 or 15 million people in Ontario, and most people, adults, might go through several cars in their lifetime, and all the commercial vehicles or not, you can see like eventually you're going to run out of license plates. And so they do need to keep coming out with new formats of license plates to so they don't have to reuse them over time. Let's do another example. So sailing ships send messages with single signal flags. In case radios break, this is a way to communicate if that technology is down. So we're going to look at how many distinct signals are possible with a set of 4 distinct flags, if you have to use at least 2 flags. So let's have a look at this. So let's say we use 2 flags. How many different signals could you make? Well, there are 4 distinct flags, and we're using 2 of them. There's 4 options for the first flag and 3 options for the second flag. That would make 12 options altogether. For 3 flags, a similar calculation: 4 for the first, 3 for the second, and 2 for the last. Gives you 24. And for 4 flags, you can probably see where this is going. You'd have 4 options for the first, 3 options for the second, 2 options for the third, and only 1 option left for the last one. And that gives you 24 as well. So the total number of different signals you can make, if you add all those up, would be 60. 60 possible signals you can make. So in this example, We found out all those cases. In each individual case, used the fundamental counting principle, and then we added them up. This is an example of the additive principle, or the rule of sum. And we're going to relook at this later on. But this is also, it's also similar to the additive principle we use with probability. But if you can break a counting problem into separate cases, like we did with the last one, with 2 flags or 3 flags or 4 flags, you can do each case and add the results. So we're going to call this the rule of sum, and we'll revisit a bit more in a few days. Let's look at another example. So say we have a lost and found bin, and there's 8 pairs of shoes in there. So that's 16 shoes in total, and there's a left shoe and a right shoe. So they're kind of 16 different shoes. So let's say a student reaches into the bin, removes 2 shoes totally at random. We're going to find out how many ways the 2 shoes can be unmatched. So there's a lot of ways that can happen. Sometimes it's actually easier to find the number of ways they can match and use an indirect method to determine how many are unmatched. So let's do it this way. So let's think about how many total different ways that we could pull out 2 shoes. Well, for shoe, I'll just write first and second here for this one. Well, for our first shoe, there's 16 shoes. There's 16 shoes to choose from. And then for our second shoe, there's 15 shoes to choose from. And that makes a total of 240 different ways that you could pull out 2 shoes. Let's think about how many ways though they can be matched. So let's think about how many ways you can have a matched pair. Just like before, there's 16 different shoes you could choose from. But if they have to match, there's only one option for the second one. You have to pick that. Whatever you pick for the first shoe, there's only one possible choice for your second shoe that makes a match. And that gives you 16 possible ways to make a match. You can choose the left shoe then the right shoe, or the right shoe then the left shoe for all 8 pairs, so 16. And so we've actually answered the question. The number of ways to get 2 shoes that aren't matched is just the total minus the number of matched possible matches. 240 minus 16, 224. 224 ways that you can pull out 2 shoes and they can be unmatched. This particular way of doing things is called the, we just did our solution on that one there. This is known as the indirect method. It's similar to what we used in probability with events and their complements. You also might call this the rule of exclusion, because we didn't directly find the number of unmatched pairs. We did it in an indirect way. We got the total. We found the number of matched pairs, which was easier to do, and then subtracted them. So this indirect method can be very useful at times. So let's do a quick summary. So if you have a problem and you're looking for counting the number of outcomes in an organized way, we actually looked at 4 strategies. 1, you can always make a tree diagram. Now they can be a little cumbersome. They can get very big if there's many different stages and options at each stage. The tree diagram we made earlier, wasn't too big, so that was manageable. You can use the fundamental counting principle. For more complex problems involving cases, you can use the rule of sum or the additive counting principle, and we will revisit that later on. And for problems that appear to be complex, you can often make them not as complex by using an indirect method, like we did with the matched pairs question. What I have for you guys is, as far as practice goes, I have these questions here actually from my in-class course I'm teaching data management. For you guys, your next steps would be the following. On our online classroom environment, there is a formative quiz with 5 organized counting questions for you to try. Just a reminder, they will not count against your mark if you don't do well, but they could help your mark if you do well. So it's low stress. Just try to apply what you've learned. And then I've given you guys a PDF of lots of organized counting questions. So give that a try. Solutions are on the PDF, but please let me know if you need a hand with anything, and I would be more than happy to get back to you, shoot a video of a solution, post solutions online, whatever you need. So have a great rest of the day, and we'll see you guys online.